Okay, bond energies and bond length. In the last chapter, we did some calculations with enthalpy, enthalpies of reaction. Yeah, we love that. Okay, so this is a different way we can estimate enthalpy changes for a reaction. It takes energy to break a bond. Okay, so what we call a bond energy is the energy needed to break 1 mole of that bond in the gas phase. So bond energies are always positive. It always requires energy to break a bond. If it released energy when you broke a bond, why would it stay bonded together? It wouldn't, right? So it's always a positive thing. The more energy it takes to break the bond, the stronger the bond is. So here's an example. If we take a hydrogen chloride molecule and we break the bond between hydrogen and chlorine to get a hydrogen atom and a chlorine atom, we see an enthalpy change of 431 kilojoules. It's positive because you have to put that in. You have to invest it to break that up. Compounds that have stronger bonds tend to be more stable because it's harder to break them up. They're less reactive. Of course, bond energy varies a bit in different compounds. So here if we look at, this is methane. So we're looking at the carbon-hydrogen bond, but we've got 3 hydrogens on the carbon. To break that bond is 438 kilojoules per mole. If we look at a similar molecule where we have 3 fluorines on the carbon, it's 446. It requires more energy. If we put 3 bromines there, it's less energy, 402. And if we've got 3 chlorines, it's 401, almost the same. That's to break this carbon-hydrogen bond. The strength of that bond depends on what else is going on in the molecule. So usually what we do is we just look at an average bond energies. They measure them on all kinds of different compounds and average them together in whatever special way they want. They put it in a table and we just go look it up. So we say the average carbon-hydrogen bond energy is 414 kilojoules. That is not just the average from these, that's the average from a whole bunch of things. Double and triple bonds are stronger. They have higher bond energies than single bonds. Ta-da! So here's a table giving average bond energies. One thing I'd like to point out in here is this asterisk. So a carbon-oxygen double bond has a bond energy of 736 kilojoules per mole. But if you're looking at carbon dioxide, it's 799. It's a big difference. And carbon dioxide is a very common compound, and so that's why we kind of singled that one out. The rest of them are just looking at average things. But if you look at like this carbon-nitrogen bond, single bond, double bond, triple bond. It's almost double in energy and triple in energy. Not quite, but roughly. Okay. So we just go to look at this when we want a bond energy. So how could we use these to estimate enthalpy changes? Well, breaking bonds is endothermic. You have to put energy in. But when a bond forms, it releases energy. You can't have energy being created or destroyed by doing a process and undoing it over and over again. If you could make energy that way, it'd be really awesome, but you can't. So you break the bond, you have to put energy in. When you make the bond again, that same amount of energy comes out. So it's just opposite in sign. So all we're going to do is we're going to add the energies for all the bonds broken and all the bonds formed. So the sum of all bonds broken is a positive, and the sum of all the bonds formed is a negative, and you look at the overall total. Here's an example. So methane and chlorine reacting, and they're going to form chloromethane and hydrogen chloride. Well, in order for this to happen, we have to break a carbon-hydrogen bond. So we have to pull this hydrogen off, and we have to separate these 2 chlorine atoms. So we have to put energy in to break those bonds. And then we form new bonds, so the chlorine combines with the hydrogen, and this chlorine combines with the carbon, and that releases energy, and it actually releases more energy than we put in, and so it's overall an exothermic reaction. So we add up the energies needed to break the bonds. These would be bond energies, but negative, because it's being released. We add those up, and then we just sum everything up, and that'll give us our enthalpy of reaction. So we talk about chemical energy as potential energy, and the energy is stored in the chemical bonds. What we really mean is that in that compound, there are relatively weak bonds, and when we break those, putting energy in, it will react in a way to form stronger bonds and release more energy than we put in. So it's actually the forming of bonds that releases the energy. This is why fuels, like gasoline, tend to be very reactive, right? And they're really dangerous too, because they're ready to release lots of energy by forming stronger bonds with other things. Okay, so a potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. We need a balanced equation first off. So methanol, CH3OH. What's this going to combine with in a combustion reaction? Oxygen. Got to have oxygen for anything to burn. And what are the products? Water and carbon dioxide. You only get carbon monoxide being formed when you're not getting enough oxygen in there, and that's why you're not supposed to use your propane grill inside. Don't do it. Carbon monoxide poisoning is no fun. I've had it. It's terrible. We've got to balance this too. So one carbon. 4 hydrogens and 2 hydrogens. So we can fix that. Go to here. And then we've got 2 oxygens and 2 oxygens, total of 4 on this side and 3 on that side. Odd even problem, double everything, get rid of it. So we'll make this 2 a 4. And we'll put a 2 in front of this one. And we'll put a 2 in front of that one. I left the oxygen out because that's the one we're going to mess with. Let's check and make sure that we didn't mess up carbon and hydrogen. So now we've got 2 carbons and 2 carbons. And 2 times 4, 8 hydrogens and 8 hydrogens. So we're good. Now we can deal with the oxygens. Now on this side we have 8 oxygens. 4 in the water and 4 in the carbon dioxide. 8. And over here I have 2. And I've got this one I'm messing around with. So I need this to be 6. So put 3 in here. That's a review from a different chapter. Okay, using bond energies. What we have to do is we have to figure out what bonds are being broken and what bonds are being made in this reaction. I think it's easier to just say, well, let's just break all the bonds. Let's break all of them and then make all the new bonds, right? Less thinking. I'm generally for that. We do need to look at the Lewis structures for these guys because we have to know what kind of bonds we're breaking and making. Is it a double bond? Is it a single bond? What's it between? So I'm going to spare you all the tedium of drawing these Lewis structures. So there's methanol, and here's oxygen. And we've got water. And carbon dioxide. So if I'm going to take this molecule apart, there are 3 carbon-hydrogen bonds in one of these, and I have 2 of them, right? So I'm going to break 6 moles of carbon-hydrogen single bonds. So 6 carbon-hydrogen bonds. And then I've got 1 carbon-oxygen bond in here. I've got 2 moles of that, so I have 2 carbon-oxygen. And then I have 2 oxygen-hydrogen. And I'm running out of space. I also have oxygen double bond. How many of those? 3. Over here in this oxygen, each oxygen molecule has 1 double bond that I have to break. But I have 3 moles of that. So that's my investment. And then over here is the payoff. I've got oxygen-hydrogen bonds, and I've got carbon-oxygen double bonds. Well, that's nice. There's only 2 kinds of bonds. Each water has 2 oxygen-hydrogen bonds, and I have 4 moles of that. So 8. Each carbon dioxide has 2 double bonds, and I have 2 moles of that, so 4 of the carbon dioxides. That maybe went a little fast. You can go on YouTube and play it over again in slow motion. Okay, so this is where I'm going to cheat and use the board, because I can't remember all of these. So that's what we're breaking, and, well, actually that one is, we just have this one other one, C double bond O. So we're going to go back to the table now. So we need to find the energy of a carbon-hydrogen single bond, 414 it says. And a carbon-oxygen single bond, 360. And hydrogen-oxygen, 464. Oxygen double bond right here in the middle, 498. And our carbon-oxygen double bond is the one in CO2, because that's what we've got, so that's 799. It's CO2. If it wasn't CO2, it would be 736. Okay. Back here. So the oxygen-hydrogen bonds, this is going to be a negative now on this. I'm doing the right side first because I have a red pen. Negative 464. And the carbon-oxygen double bond, negative 799. So 8 times negative 464 is minus 3712 kilojoules. And minus 799 times 4 is 3196 kilojoules. That's also negative. So 3196 plus 3712, well, the negatives, that's going to give me a total of negative 6908. When 4 moles of water and 2 moles of carbon dioxide form, it releases 6,908 kilojoules of energy. Any questions? People are whispering questions to each other. That's fine. It saves me from answering them. So there's the carbon-hydrogen bond and carbon-oxygen. Oxygen-hydrogen, 464. Oxygen-oxygen, 498. This is just tedious math. So 6 times 414. These are positive because this is energy you have to put into the molecule to break up these bonds. 2 moles of CO bonds, 720. And I've got 2 moles of oxygen-hydrogen bonds, 928. And 3 moles of oxygen-oxygen double bonds. It's like going to the grocery store. Taking 4 apples and 3 oranges, and etc. Add these together. So that equals 5626 kilojoules. I have to invest. Yeah, question?
How come on the left side you don't multiply the 3 by 2, but on the right side you are? Like, should it be 6?
This up here?
Yeah.
Okay, I did the doubling everything when I was trying to figure out what this was.
Yeah. I'm saying how come down there you left it 3, it's not 6? Yeah.
Because I have 3 moles of O2.
Okay.
Each O2 has 1 double bond.
But for the other ones you have 2 moles CO2, but you multiply the 2 by 2.
I have 3 moles of O2.
Yeah, I know, but on the right side I'm saying you multiply the 2 by 2 to get 4, and the 4 by the 2 to get 8. I don't know.
Well, because this molecule has 2 double bonds. So if I have 2 moles of that, then I have 4.
Okay.
So if I have another one of these, so this is saying 2 CO2s. I got this one and that one. That's 4 double bonds. But over here, I have 3. I just have 3 because each of them has 1. We'll go over this again. I see what you're struggling with. So I have to invest this much energy to break up everything, and this is what's released. Now, in actuality, do all of these bonds get broken? No. Does it matter? No. Like this oxygen-hydrogen bond probably stays intact, but I think it's too picky to go through and figure out, well, this one stays together, but this one doesn't, and just mess around. I think it's easier to just take everything apart, start over, start from scratch. So overall then, we have the 5626, and we're adding this negative, minus 6908. Just add those 2 numbers together. Overall, I get negative 1282 kilojoules. What's the question asking for? Enthalpy of combustion of methanol in kilojoules per mole of ethanol. This was for 2 moles of ethanol. So I have to divide by 2. Divide by 2 moles, because that's how I wrote the equation. And so divide by 2, 641. Negative 641 kilojoules per mole. And there's my answer hiding up here. Should write it down. Minus 641. Any questions? Why?
Very tedious.
It is tedious. But you could sit and do that on a piece of paper, or you could gather the materials and equip a lab and figure out how to do the reaction in a way that you could actually measure it. I think a calculator, a CRC, some paper and a pencil would be much faster, right?
Pencil will never be effort.
And really the reason that we're teaching you this is that we want you to have this understanding of what goes on in a chemical reaction. When a chemical reaction is exothermic, that means that the bonds that were formed are stronger than the bonds that got broken. If it's an endothermic reaction, the bonds that are breaking are stronger than the bonds that are forming. Bond lengths. Bond length tends to correlate with bond strength. Average bond length is just going to be the average length of a bond between two particular atoms. And again, we're looking at averages. Double bonds are shorter than single bonds, and triple bonds are shorter than doubles. So if we compare the 3 bonds that carbon makes with itself, bond length, the triple bond is the shortest, and it's the strongest. The double's in the middle, and the single is the longest and the weakest. And there, I'm not sure why they even have that in the book, but there's a list of bond lengths.